And part of the work of mine, which was already been done by the previous speaker in the morning, the keynote speaker. So I would try to rush through this because you've already been delayed and I don't want to delay your lunch further. I'll talk about basically though the topic talks about innovation in electronic design. I just thought my 50 years of experience, I would be completing 50 years in another couple of months. I graduated in '63 and been a visiting professor at IIT Bombay since 1992 and a distinguished alumnus in IIT Bombay. And I started my own company in 1971 to do specialist jobs for nuclear power, defense and electric utilities. And we compete against multinationals in this country, ABB, Siemens and others, and then do specialized report system equipment. I thought my experience over the last 50 years of designing real-time systems, special products, etc., I could pass on to some of you who are now getting into the industry and wanting to do their own. Typically in electronic system and product design, you have the system or the product to be thought of in concept creation. You first think what you need to do, how you need to do, why you need to do, and things of that kind. Then you need to do a proof of concept. You'll have to make a breadboard design or a circuit design and things of that kind to show that your idea would get through and work through. Then you go into the product development subsequent to that, because the product development would now have to have some specifications or meet some requirements. If it's your own product, it's your specifications, or if it's your own system, your own specifications. But if you're trying to do the product or the system for somebody else is going to give you the requirements, or you would say, I need this, I want this, and things like that, and on which basis you would make the equipment and give it to him. So in the process, what all you need to take care of, what I would talk a little more about it. Then having done the basic design and got it principally approved by the user or your own client whom you think would need that product that you're going to give, you would assemble the whole system and try and verify whether the system is working to the final specifications to what you had said you would do. And you would perhaps need to get certification done by others. Like in this case, in our case, we are doing some job for nuclear submarine, in which case we need to get those EMI EMC done. And it's 3 years since we are trying to do the EMI EMC in this country. Everybody says he has a facility, but when you go and ask him, he doesn't have the proper facility at some point of time. He doesn't have the power supply. He says, I have 461C, I don't have 461E. Or if he has 461E, he doesn't have 461FC. And the client is not clear what he wants. So it goes on like that at the end of the day. And you finally, having done all this, you make your pilot batch, get it through, run through the whole thing, and then you make your full-scale launch if it's your own product. Like our friend said a little earlier, that he was a 30-second iteration of his project for a simple, what you think is a simple blood glucose measurement. So we need to look at things a little more this. So I just wanted to go back to Wilbur Wright when he said, if you are looking for a perfect safety, in our case, perfect design, because he was trying to ensure a safety, the airplane going in safety and coming down, taking off and coming back to the ground. Whereas we, as product designers, we are ensuring that our design should work properly and not cause problems for others. Because today's condition is that thanks to the Consumer Forum and other legal conditions, you are fiducially responsible. When I say fiducially, you are legally responsible to give what you had said you would give, or you would give what the client wanted you to give. He can take you to the court of law and ask for damages if there's any problem that your equipment is not meeting his requirements, or your equipment is not meeting the requirement you said would meet when he buys the product from you. So we need to get that in terms of our design. So if you're not able to do that, we can go bird watching. So what are the critical design phases that we need to look at? What is the final design? what is that final thing that you have got in mind? This is what you would do. Then who is going to do it to help you to do the finalized design? You can see in your own organization, the marketing guys will be there, the manufacturing guys there if it's bigger organization, bigger projects. And other people like the test team, your industrial designers, if there's a equipment has to be specially taken on and given to different locations, like what the first speaker talked about, the product for the space, what kind of logistics will you use to ensure that the product is done, taken to the place? If you talk about the product being made in Bangalore for the ISRO, it is not in Bangalore that they are using the product. The product is going all the way to Chandrapur in Orissa to be put on, or in Trivandrum for launching the thing. So you need to ensure that the product that they make here has to be taken to that locations in a proper conditions, so that the equipment that you have taken so much care to make, as whatever you talked about from day one when they think of a product to day, I don't know, 2 years, 3 years, 4 years, 5 years, at the end of the day they have to take this product to finally put inside that launching rocket. Then you have to take care of all that. After doing all this, whether you would finally go ahead with the project, who is going to take a decision? Somebody has to take a decision. There are minor problems. Says, okay, we'll take care of in the field. We could launch the product. A friend of mine has done that. He is having problems now. The client has taken the product. The client says it doesn't make 4 kV lightning signals that are coming in high-rise buildings. 3 years ago, quite a lot of people in Bombay lost their television sets and their laptops connected to the mains because of a very big lightning which came in the Mumbai city. So today's, like what you were talking about, the ESD and the lightning, the products can get damaged, and then earlier the specifications were 2 kV, now the specifications have gone up to 4 kV for household appliances. I am talking about the appliances that you use in your house, the water filters that you use, electronic water, the ultraviolet water purifiers that you use at home. That equipment has to withstand 4 kV of surge for 1 microsecond, 50 microsecond that the surge goes off in the case of a lightning. So we need to find out who is going to take this decision. Okay, it's accepted, gone through 2 kV, let me launch. I don't think much problem will happen. If there are 100 of them fail, you're again going to talk to the consumer, is going to go to the court. You also have to replace the equipment. You have to find out why things happen. So it's going to be a bigger challenge to find out. Earlier it was okay, I would put it and then you would be only giving to known people. Now today, you are making the product and you are selling it through distributors, you are selling it through large companies like Godrej, Bajaj, etc. So your need to ensure that the product that goes is not your product, it is going as a Godrej product, it is going as a Bajaj product or somebody else's product at the end of the day. So you have got to protect not only your name, you have got to protect their brand name. If they fail, they can sue you, but you can go home. But then they will be sued and then they will know where they will have to go. So how do you do all this? You have to go through various reviews that the previous speaker talked about. Various review boards are there for different components and things like that. In your case, you will do it for whatever product that you have listed. How will you do it and why will you do it? And again, you will have to do the evaluation test. When I talked to you about this 4 kV test for this ultraviolet purifier, we tested at 2 government labs. The equipment passed for 4 kV. We gave it to the client. Client had his own equipment with him and the client says, sorry, it is not passing. So we really don't know whether we have done the right thing or the wrong thing. And finally, we have to change the components to ensure that that equipment passes the test equipment that he has. He says this is the same equipment the other guy has, but it has passed in the lab in a government department, but it has not passed the lab in his own incoming inspection unit. So when all this is over, you complete the phase and then the design is finished, then you appropriately test it and then you find out how to go for the final manufacture. Then having done that, having done the design, then and got that, how is the product handed over to the final manufacturing? Because once the design team has gone through, done everything else, and finally got the product through, and they are given the PCBs, housings, testing procedure, storing procedure, and things of that kind. You have to hand over the thing to large scale production. If it's like an ultraviolet, this you are not making 1 to 100, you are making 10,000 a month, 20,000 a month. The requirement in the country is around 200,000 a month. So there are around 20 manufacturers making the same thing. So if you are going to give that into production, you have got to also ensure the kind of component that you will use. Some components have long lead time, some components are very, they are available across the counter and things of that kind. Again, you will get involved with the rest of the people when you hand over the thing, the marketing team will come. When do you want it? We get an order from Emerson for some products every 15 days. And after about 2 months, they say, sorry, we don't require this for under 6 months. It's not going in the market. It's not available in the, nobody's picking it up. Or there is a slack season like refrigerators. During the monsoon, nobody wants refrigerators. Some companies would keep them, make a minimum amount of this for some odd reason, but when the summer comes, they want all the 10,000 pieces or 100,000 pieces to be delivered in 2 months' time. So you would have to go through all those portions, and particularly in electronics, this is something most of us don't understand. Most of us would have to use as part of our power supplies electrolytic capacitors. The electrolytic capacitors have, unless you use highly reliable electrolytic capacitors, normal capacitors that you would get in the market, have a shelf life. That is, if you say that you have got a 100 microfarad capacitor, you would have formed, when the manufacturer gives it to you, he has formed the film inside and given it to you, so it is around 100 microfarad. Maybe the variations in tolerance in capacitors for electrolytic capacitors is minus 50 to 100%. That is, if it's 100 microfarad, the capacitor could be 50 microfarad, it could be 200 microfarad. The manufacturing tolerance are fairly large. Even normal capacitors also, the manufacturing capacity tolerance are plus minus 10%. When you say 1 microfarad, it is 0.9 microfarad or 1.1 microfarad. So when you use electrolytic capacitors which are formed, and if you had made a product now, and the product has not been used for nearly 1 year, 1.5 years, and things of that kind, and subsequently used, the capacitor is no longer an electrolytic capacitor. It is just a box. It may be 1 microfarad, 2 microfarad, 3 microfarad, not 100 microfarad. So when you really start using an equipment, you make a power supply which contains a lot of those capacitors. You have kept it inside and you have not used it, you have used it as a spare, which happens in our case. We do a lot of specialized systems for nuclear power. We delivered some systems in 2004 for Rajasthan Atomic Power Project. The system got commissioned in 2009. Rather 2010, sorry. So they had kept all these equipments in various stages of when I say not in use, I will not say disuse. They were not in use because they are not powered on and they are waiting for the things to come and things of that time. And quite a few of those power supplies did not work the moment when you start charging, when you put them on again. You don't get the same kind of response that you would have otherwise got from a power supply. Ripple should be less than 0.5%. The regulation should be X, Y, Z, and things of that kind. So you need to reform the electrolytic capacitors under the conditions in actual use. So what you would have to normally do is, if you have a zero, it's a 240 volts AC power supply, you have to go back to zero, raise it to 240, keep it for some time, come back to zero, go back to 240, come back to zero. Then the power supply will work satisfactorily after 2 or 3, forming the films. So these are issues which one doesn't understand, because the customer will say that your equipment failed. He also does not know why it failed. At times, you also don't know why it failed. And it is going to be difficult. Then you will say, okay, I'll change the capacitor. It may be easier to do that. But going and changing a capacitor in some of the equipments is not very easy. Because you would change the conditions, you would have done some tests like what he talked about, the radiation test or AMI, MC test. And the moment you change some values and put a new product inside, 2 years down the line, 3 years down the line, you don't get the same size of capacitor. The capacitor is either small or bigger. So you might have other issues coming into picture, so you've got to be careful about that. So these are issues that we have to validate the design, close all open issues. In many cases in electronics, particularly when you are talking of systems, when particularly you are talking about embedded systems where you have a lot of programming going on. Not all of us are able to test all the parts simultaneously and get everything through. Because we do some program, we say, okay, I put this in, put this input, put this output, check whether everything is working all right. It's for us when we try to do a system in 1989 for remote control of electric substations through telephone wires, where Bombay's substations which supply 33 kV to 11 kV and 11 kV down to onto the streets. We had around 22 stations controlling around 600 odd breakers remotely through telephones. It took us nearly around 4 months of validation to ensure that NI operator remote control, if I am saying it, I give an on signal, the breaker will become on. If I give an off signal, the breaker will become off. By chance, I give an off signal to the breaker, which is off, and by it becomes on, somebody may be working on the line and he might get electrocuted at 11 kV or whatever. So one has to look into a lot more of those things, and if there are open issues, somebody said, I'll look into it tomorrow. You have not documented that he will look into it tomorrow. You have assumed that he has looked into it and you have got the thing through, then you had it. So you have to ensure that particularly embedded system design guys, they have to take care of these issues properly, because in today's condition there are not one person working on an embedded design, you are working up 2 or 3 or 4 people working together. And in that process you have to ensure that the 4 works as a team and ensures all open issues are closed. So if there are other issues, who will do is going back to the same kind of marketing and things of that kind. And why? Now here is the next part of the game, which is the quality guys who come into picture. Till now you as a designer did all the tests, validated and things of that kind. But finally it gets into the production and the product has to go out of your door. A third party guy or your own person who is as independent as possible. If the quality guy is reporting to the manufacturing, the quality guy the manufacturing guy will say the product has to go out tomorrow, so please check fast. And so this guy has to do some sampling, not take the totality into consideration. So those would be involved. And then, when you say really put the equipment on, it's where the equipment is only isolated equipment working in a power supply in a lab, or is it a power supply working as part of a system? In each case, you have to ensure that whatever you do, the power supply has to finally work in the field, and there you have got to ensure the integration properly takes place and the testing is done for all conditions properly. Because in our case, when we do a project for nuclear power, it takes nearly around 7 months to get a product through. When I say 7 months, we get a testing done through to the requirement of this. And in nuclear power, a QA is the most important person, unlike other manufacturing organizations. And when you take this product out, is when the customer says, yes, I am happy with what you have done and I am willing to take it in lots 1, 10, 100,000, 10,000. So all that starts is, what is that set of requirements that you get? I can have various adjectives of these requirements. It is correct, the requirement is correct, and what has been given is correct. So you will be able to meet the need of what you want to do if it's your product, or if it's the customer specification, whether it meets his specifications. Does it meet? Is it unambiguous? We have problems. Customer says that I want this, I want this, I want this, and most of us as engineers, we are not able to write our specifications in proper English. As technologists or engineers, we have got to be precise. The English has to be unambiguous. When we say A, it is A, it is not B. It is not A dash, it is not A2 dash. It is just A. Like perhaps 3 days ago, you might have seen the papers with that A because of whom? The guy who died, the guy who went to the moon. He said, in his speech he had said, airman. He is an engineer, mind you. But what was recorded was M, not A was not recorded, it was just man was recorded. For which he was upset, because he thought he was taking the credit for that. He said it could have been anybody, not A man, not himself, but it could be anybody else. And that's the reason he did not come immediately to this to wish people. Then the next is it complete? Is it in totality? Most of us engineers, we think, I have told you, I have written it, haven't you understood it? There are lots of things, because most of us engineers don't cross the T or put dot over the I. We think that he is who is sitting in front of the computer making operations. He is not the guy who had asked what that equipment should do. He is a guy who is using that equipment, and he is not necessarily know all of what things go on, except that he needs to ensure that if he is giving a command or looking at an alarm, he is looking at the specific alarm, he is looking at a specific command and giving it. The fourth is around consistent. This is a major issue with many cases. We write specifications of, if you see government specifications, I don't know, there may be government officials, pardon me. If you see a government tender coming out, you have 100 pages of you can't do this, you can't do this, you can't do this in terms of commercials and other things, etc. And if you deliver the product, 1 week later they will cut 10%, 20%, whatever it is. But in the specification will be only 2 pages. It may be a 1 crore product, a 10 crore product, and a 1 lakh product. It will be only 3 pages. Then subsequently they will say that, no, you have to add this, you have got to do this. They go. Then they say, I have given that IEC specification, I have given IEEE specification, I have given different specifications. It is for you to go back and tell them, say, look, IEEE specification talks like this. This is not, is that what you intended? The IEC specification talks differently. Is that what you intended? So you will have to go back and ask them and ensure that there is no difference in what they specify and what you have assumed that they specify. So I have got a recent case where we are doing a job for around 60 lakhs of sensing for a nuclear submarine. They said we have had the design ready, all that you have got to do is populate the board, all that you have got to do is this. Now it's 4 years. He says, didn't you read this previous annexure? Did you not read the previous annexure which they were talked before, which was not part of the order? So one has to be very clear when you do such kinds of jobs as a designer. And then, subsequent to that, you'll have to verify whether whatever you have done the software, you write a test software, then you find out whether it works satisfactorily, then prove that it works satisfactorily. Then whatever you have done at the end of the day, the product that you have verified and the specification that you have agreed to meet and it meets, you have got to ensure that whatever equipment that you use, whatever testing that you do is traceable, that somebody else can repeat that product. Because when you use an equipment, you say I used A equipment, B equipment and C equipment, and if somebody else has used the same A, B, C and it doesn't get the same result, you have to find out why. Like in our case, when this 4 kV test was done, 2 government labs passed the test and 1 did not pass. The main customers did not pass. The one major thing is, in today's conditions, thanks to embedded design, people expect you to change programs because they say, I wanted it, and they finally, when they put it in the equipment or the product into use, they find some changes that is required. Then you say, sorry, I can't do it. But you have to find out and go back and find out whether would he need change by any chance when you use your equipment. And in that case, is it possible for you to modify? The basic circuit, once the PCB is made, is going to be difficult to change. Like what's happening in our case, because in the case of the ultraviolet condition, we have to change a full board with around 120 components. All for that sake that the 3 components that we used, which we thought had passed in the government lab, did not pass in the customer's lab. And he had not specified this test as a part of his original specification. It's because of relationship we agreed to do it, we have made changes. But now, if I need to add that on a 200 rupee component, I have to charge him 100 rupees just to put 3 more components, which he is not willing to pay. So those are issues. So at the end of the day, if we are doing a product for a customer, and customer is saying that I want this, please go back and find out what he needs, not what he wants. Because you've got to ask him where he might say, give a specification, you give this product as per this, I don't have a problem, I'll use it. But at the end of the day, you as a designer will realize that once you give the product to him, he says, I want this, or can it do this, can it do that, etc. And at the end of the day, so it's, if you are an independent designer and trying to do a product development for somebody else, please go back and find out what the customer requires, which is different from what he wants. Please. This is one major issue that one has to. This has happened with us. 1 year ago, we delivered a panel to BRC. They accepted, tested, everything was through. Now, having thought about the problem for another 6 months, the second panel was to go last month. They say, no, we want changes in software. The changes in software is going to take me 1.5 months. It is going to add up some components in a board. So who is going to pay for all this? This is despite the fact that we know BRC well, we know the people there well, but it still happens. So if you as a designer tomorrow is going to get into this problem, be aware that you would get into this problem and at least try to, as the previous speaker talked about mitigation, you find out how will you reduce your losses or increase your profits in the day. Now, one more area which we have been a specialist in analog design for all these years. That's one of the reasons that we have been able to do a lot of work for nuclear power and for defense, DRDO guys, for the missile launching system or for the various sensing products, circuits and things of that kind. One problem with all of us is that all of us feel digital is easy, digital we can change, we can do all that. But at the end of the day, real life is analog. You have got to sense, you have got to take the signal in, push it through some kind of circuitry, and then subsequently do all that you do with analog to digital conversion, do all your DSP, XYP and things of that kind. And again, at the end of the day, you will have to again convert it back to analog in some cases, where if you've got to give control to another product or another system, or you could do it digitally if the other product can accept a digital condition. But here, the major problem is, what is, when you design a circuit, how much of analog and how much of digital? Because analog is that once you have made your major decision in design and ensure your design is okay, you don't have to do much changes and you are able to give an output as what is desired. Of course, there will be a lot of changes because of temperature, a lot of changes because of other changes in voltage, changes in things of that kind, which you have to build in as part of your design, which may not be necessary in the case of a digital. But in the case of analog, you have to take care of all that, ensure that the output that you had planned to give for that particular module or box or whatever it is within the specification that you have agreed to meet. Be it temperature, as the other gentleman said, minus 5 degrees to 55 degrees or 10 degrees to 40 degrees, etc. If the temperature changes, if the battery voltage changes by more than 10 or 15 or 20 or 30%. One case we remember, way back in 80s when the first time when we developed transducers for monitoring high voltages, power of 400 kV stations. They said it is 48 volts plus minus 10%. So 48 volts plus minus 10% means what? 48 plus 4.8 is around 52, 53. Minus is what? 44. But if you really take a battery, 24 cells battery, it's normally charged to not 48 volts. They say 24 into 2 is 48. But actually it goes to 51.2 volts. And when you put the battery on boost charge, that is at the end of the week that the battery is getting discharged, the battery has come down to 49, 48, 47. You no longer can use your system otherwise, because most of the telecommunication system which uses the same 48 volt DC power supply, in many cases, be the cellular radio or be the other electronic equipment elsewhere for communication, they all work on 24 volts cells, 24 cells battery, which is 48 volts, typically mentioned 48. The normal charged voltage is 51.2. The moment you remove the battery charger from the thing, it will go down to 49. But at 51.2, when you put it on boost charge, that is at the end of Saturday, you put it on boost charge. It so happened, on Saturday morning somebody put on boost charge, he didn't come back to the station back. He came, Monday was a holiday, and Tuesday morning he came back and found out the battery was on boost charge. You know what's the voltage of the boost charge condition for battery of what, 24 cells? Any guesses? 66 volts. And why is the specification of 53 volts, 48 plus minus 10%? And why is 63 volts? All our 100 transducers got burnt. So subsequently we realized that people do not know how to specify. So we started making, and then if by chance the battery is not charged, the battery charger is off for any conditions, AC is off, something has happened, the voltage can go down to as low as 38 volts. We have 51.2 volts on charge, uncharged, I mean the normal condition is 49 volts, can go as low as 38 volts. And as far as the client is concerned, I have put the battery on, your system is on, you have to ensure that your product works. So since then, we have been designing our equipment because we don't expect these guys to specify properly. And at the end of the day, if the equipment is damaged, he's not going to tell me I put it on boost charge. It's luckily that we knew the chief engineer. He came with us to find out why 100 transducers got failed. And then he realized what mistake had happened. He went through the whole attendance of the guys who were maintaining the system and this, that kind. We got paid for that 100 number transducer. That was another part of it. But since then, we have been designing our systems from 35 volts to 70 volts. So that in any condition, even because as a designer, you are not have to make it foolproof, you are going to make it foolproof. That's the major problem. All of us, because we don't know what the other guy really knows or he doesn't know. So beware of that point, which we have learned through hard ways. It is luckily that the chief engineer agreed. Otherwise, I would have spent, it would have been close to around 9,000 rupees per transducer in those days. Now the transducer is now available for 3,000 rupees. 9,000 into 100 numbers, you can understand what kind of loss I would have gone through. So we have to, in the case of analog, we have to work out the analog part of it. We have to find out what kind of analog circuits, what level of analog circuits will you use. And you also have to find out what kind of digital filtering that you will do if you are not doing analog filtering, and what level would you do. Or alternatively, can you think whether I can increase the signal level to a sufficient level by using an amplifier and then ensuring a better, not so costly A to D, can I use a lower A to D converter and still get my job done. And in the case of this, what kind of reconfiguration would you have to do, what kind of reprogramming that you would have to do in future. So these are issues that you will have to take care of when you have analog and digital together in a product, which happens in many cases today with embedded design. Because we are trying to do this, all this for cost reduction, or we are trying to use, we don't want to do unnecessary functions and that, and in the process, you are going to choose. So in the process of choosing, what will you choose? That is something you have to figure out. This is a typical development cycle, what we call waterfall technique. That concept, you do a prototype, you check with the customer evaluates your product, and you go back to redesign. And then once that one cycle is through, then perhaps you would make the complete design and send it to the final production mechanism. This is another way of looking at the same problem. You start with the requirements here. I don't know whether this is seen from the back. You will start from the requirements of the spiral. And perhaps you would go through the same thing again and again. You see the spiral, one spiral, the second and the third. Finally, the final evaluation is the last spiral. It's not once, twice, thrice. It could be, as the previous speaker talked to you about, the typical iteration that happens in a space electronics is close to around 15 times. Here we are just talking about 3 times. In the space, the equivalent talks about 15 times. In the case of a nuclear reactor project that we are trying to do for them now, for the latest 700 megawatts coming up in Rajasthan 5-6 and Kakrapara 3-4 near Surat. One product we are doing it for the last 3 years. Because suddenly after the Fukushima accident in Japan, now they say that the accident which happened in Japan was because of loss of cooling. That is, the cooling system did not work through because of the batteries. I mean, there is no water for the diesel generators to start on. The diesel generators failed, hence the equipment could not be cooled, so the reactor melted, and so many things happened there. Now they are trying to use a different kind of thing that they will cool the reactor externally for a different mechanism. So the products which are in some part of the equipment, in equipment which are in some area, have to go through a temperature of when they put the cooling water inside the reactor, which is already hot. The temperature can rise up to 160 degrees centigrade in 1 minute. And there will be water on top of it, so that you can understand what will be the humidity. The temperature is 160 degrees centigrade. The humidity will be close to around 95 to 99%, if not 100%. You have to ensure that your product has to go through this and withstand those conditions. And it is after the whole thing process is over, and then you start a product again, the reactor again, your equipment would have to work satisfactorily. So all those this would go through. So this is one way of looking at a problem. If you really look at this, maybe many people would have talked about build quality. As far as the electronics is concerned, it should not be an afterthought. It has to be part of your own design right from the day, from the point that you talk about. This is the concept. From the concept, your quality assurance should have to be there. It's not that you do the quality assurance after you made the product and you call the guy and say that you test it for 50 degrees, you test this, put this equipment for 4 kV test or 1 kV test or whatever happens. But you have to start looking at right from the concept space. Then when you do the analysis, then you write the requirements. Whether the requirements are okay or not okay, whether they are ambiguous, not ambiguous, they are complete, and things of that kind. Then you get into the design, again involve the quality. Then you do, when you do your, in this case of software development, your verification and validation of the software has to be a part of right from the beginning. It cannot be subsequent to that you writing the program and then you ask somebody else to validate or verify, or you do your own verification and validation. Because in our equipment, whatever we do, we have got to make a test procedure first before we make the product. And this test procedure will have to be either what all the various tests that you would do to ensure that the normal production goes through, the qualifying requirements go through. Unless these test procedures are cleared by the intender or by the user, or in your case, if your product is your own product, your own quality assurance guys should have to clear that yes, if we do the product as per this test procedure, the product will go through without much of a problem in the field. So it goes through the case of testing, then when you do the verification part of it, and finally you are given a product. In our case, as the gentleman from ISRO talked to you about, the equipment has to work for 15 years somewhere in space. And in our case, the equipment will have to work, in the case of a DRDO, either in the ship for 15 years or more, or if it's a product which is going in a tank or any other missiles that it will, it has to be a missile if you really take. When would you use a missile? At the time of final firing. But the missiles are stored for 10 years, 15 years, 20 years. You have to ensure that you would test them once in a while. You would not be continuously testing. You can't do that. You can't arm the missile. Then you don't exist, I don't exist. So in that process, what you need to do is you have to ensure that you test the missile and basically expect the electronics of the missile to work, the batteries of the missile to work and things like that. And they have to work for 15 years. And you will have to put the missile on the whatever launching pad that you do, because we have done designs for BrahMos mobile launching vehicles, we have done the electronics for them. So we understand that the point at which you lit or make the missile go on, it has to fire, it has to work. It could be 15 years. Or alternatively, the same missile could be used in Rajasthan at 55 degrees centigrade, or it could be used in Kargil at minus 20 degrees centigrade. So you have to ensure all these variations are taken care of when the equipment works, and finally when it to be maintained. When I say maintained, these missiles have to be maintained before they are used. There are other equipments which have to be maintained while in normal use. So you will have to take care of all those things. There again, you will have to ensure your quality assurance takes place. Till now, not many products are being made in this country. People, when I say made in this country, last 10, 15 years, there are limited people doing it. You would say Bharat Electronics doing it, or BDL doing it, etc. And bulk of Bharat Electronics is home-made, or they had some designs which are available from RCA and others. But today is that we are making our own products, our own design, making improvements on them and things of that kind. It's now that we are trying to understand, because till now when we get equipment from others, we knew what the equipment would do, we knew how the equipment would do, but we were really not worried about why, why did that designer in US or in Europe or XYZ choose a particular capacitor, choose a particular material for this condition. You choose a particular, because that's why was not known to us. We were all these years given technical know-how. We did not know the technical know-why. That is, means the normal people, the engineers down working in these organizations, they had to find out their own whys. If something failed, they will find out why it failed, and based on that they would kind to do it. But now, thanks to most of you going into higher education, doing your MTechs, doing your PhDs and things of that kind, the part of finding out why you need to do something is now available to us, and then we could improve much faster. I just got 2 more minutes. I just wanted to, because the theme was Electronics Rocks 12, I thought we should pay homage to those rock stars of electronics, particularly in analog devices, without whom these 3 guys, Bob Pease, who wrote the Pease Porridge articles in EDN, Electronic Design News. He was earlier with Fairchild and subsequently with National Semiconductors. And he is just a basic electronics engineer from one of those American universities, but a guy who had gone down to the deep of analog electronics. If you are really interested in analog electronics, please go through the various Pease porridges available in the archives of Electronic Design News. And the next guy is Jim Williams, who was a technician at MIT. He was running a lab in MIT. His lab 20 was a famous lab where many people went and learned about analog electronics. And subsequently he joined Linear Technologies, and as also part of National Semiconductors, as part of National Semiconductors and Linear Electronics. He has written a lot of application notes how you should use analog devices. A lot of people, American engineers working in Silicon Valley and elsewhere, have been trained by him. He's just joined, he's not an engineer by what you call by education, but he learned all his electronics, and he was a remarkable guy, and Last year, June, he died, and Bob Pease had gone for his memorial, got out of the memorial and was on the road. He was killed by an accident. They were together as colleagues for nearly around 20 years. But for Robert Widler, maybe some of you who have done your masters in embedded systems or electronic design or things, etc., would have known Widlar's circuit for both current meter, and he was the first guy to make an op-amp together. And but for James Kilby, our integrated circuits wouldn't have been there. He was the first guy to put transistors and everything together in one, made the wiring inside a chip, which was not there before. That was in the year 1956, and he died 2 years ago. And for all that you guys were writing embedded programs or programs in your computer, C, C++, Java, etc., we all owe our gratitude to Ted Hoff, who was just to started with as an intern in Intel, then became an engineer and made the first 4-bit microprocessor at the request of a Japanese company which they wanted to upgrade their calculator. But of course, that did not happen. And somebody in Intel realized, because Intel till then was a memory company, it was not a microprocessor company, it was a memory company till then. And thanks to Ted Hoff, they got the first 4-bit microcontroller. That was in 1971, November. By 1972, August, they had their 8008 8-bit processor. And June, by end of November, December 72, they had that 8080 8-bit processor. And then the world came to microprocessor in a big way using that 8085 processor. I have used around 2000 of 8085 microprocessor way back in 82. As part of your design, you've got various parts to be used. Then you have modules or parts or part of design and things of that kind. That is, even in analog circuit, you would have an op-amp, you will have a resistor, you will have a capacitor and things of that kind. At the end of the day, you will try to optimize. There's one thing which most of us have to realize: optimal of the sum, putting all of them together, is not the sum of the optimal. Sum of the optimal. That is, if you are optimizing individual resistor, capacitor, IC and things of that kind, and you say that I'm going to make an optimal product, is not true. If that was true, God wouldn't have given you 2 kidneys, God wouldn't have given you 2 lungs, God would have done with 1 lung, 1 kidney, because He's got only 1 heart which He gave you. And He gave you only 1 liver. He could have given you 2 hearts, He could have given you 2 livers, like the 2 lungs and 2 this. So optimal of the sum is not the sum of the optimums. Please bear in mind when you're trying to do your optimization, because most of you as designers, at the end of the day when you go to your bosses, they'll say cut cost, reduce the price here, reduce the price here, do this, do that, can you reduce the size of the PCB? The moment you raise the size of the PCB, you will get into problems of EM and EMC, which you don't realize. Now today's circuits are working at much higher frequencies. Today, how many analog circuits are there in your mobile phones? You think the mobile phone is only digital. There are lots of analog circuits because they are working at much, much higher frequencies. So when you really talk in terms of 4 gigahertz microprocessor working, it is not digital, it's practically analog. The signals are not that straightforward cut. So they are analog. So when you really look at those conditions, so you got to take care of all this optimization problems that you will land up.